Okay. All right. Hello and welcome to another lecture on 2DM3. We'll try to do another calc check and chill kind of session. So I'll have the slides on one half of the page and of the screen, and I'll try to do some problems on the other half. Sabah al khair to you too. Good morning to everyone and bonjour. Yes. So I do have the chat over here. If you're not comfortable talking, please just ask questions in the chat. So essentially, only the last two slides of today are new. Everything else is just trying to cover stuff you've seen, trying to remove some worries people are having. So essentially, only the last two slides of today's lecture are new. So I'm hoping we can do a lot of problems, and I'm hoping you'll ask me to do certain problems in front of you. Otherwise, I can just pick some problems, but I really would like to know what you want me to do, what you're struggling with. So yes, please let me know either in the text or tell me live. All right. And as usual, I put this lo-fi that I've here. If it gets loud, please let me know. Otherwise, I'll leave it as it is. Okay, ducks. So induction and chapter 3 are really the big parts for the upcoming midterm on Tuesday. So just to let you know about that. So in particular, some of you may not be as comfortable with implication and the replacement theorems. So we'll talk about those today and a bit tomorrow, just to get you ready. Homework 7.2 was released today, and it's due Thursday. It's not on midterm 2 for now. If that does change, we'll let you know, but hopefully, thanks, Jivan. And so we'll let you know, but you should definitely be comfortable at least up to implication. So if anything changes, we'll keep you posted. All right. So again, I'm just going to do a bunch of review just to make sure everyone's comfortable with induction at least, and hopefully we'll move on to the last two slides of today's lecture. Okay. So does anyone have any questions they'd like me to answer? So I put up some, I got some of these notebooks already for you. If you want to try doing some of them, all right. From homework 5, 6, 7, induction as well. So let me know. Does anyone have any particular thing they'd like to cover? So maybe we can.
Could we do
induction? Sure. So I opened up the induction notebook. So I'll have the slides on the side and we can look at them. Right. So let's try to prove some stuff by induction. So this is homework 5, notebook 3, right? It just talks about how the natural numbers are built up using suck and 0, and that you have this idea of proof by induction, which I tried to give you some different analogies here, knocking dominoes or climbing ladders, or if you're mathematically inclined, constant functions, so that you can look at them from these different perspectives. So hopefully everyone's comfortable with it. If not, please let me know as we're talking. So let's try to prove some of these little theorems together. Is everyone good with the font size? If you're not, please let me know. Okay. So let's all right. So I see in the chat some people want to talk about the base case. So let's start there. Then we'll talk about the phrase induction hypothesis. Then after we're done here, we can move on to absorption or nested induction. All right. All right. Thank you, Tammy. Size is good. OK. So you've used these predicates even odd a bit abruptly in the midterm. Apologies. Did not mean to make you uncomfortable there. So let's define the notion of even. Right. The numbers are, even, odd, even, odd, even, odd. They ping pong between the two possibilities, right? 0 is even, 1 is odd, 2 is even, 3 is odd, 4 is even, 5 is odd. So they just ping pong, right? So we start off 0 is even, and then the next step says we ping pong, right? N plus 1 is even precisely when n is not even, because they ping pong, right? And the only way to ping pong between true and false is to use not, right? So sometimes not is called flip, right? Because it flips the values. but very rarely. And likewise, odd numbers, they start off, the first one is not odd, and then they ping pong again, right? So that we can use the same scheme here. So here's the very first theorem. So let's show that odd is not even, all right? All right, well, odd 0, we know by definition, let me get this. We know by definition that 0 is not odd, right? So this is just false, okay? But we know by definition that even 0 is true, right? So we can continue that way. So we can say L not true. So notice what I'm doing. I started from the top, I made it to false, I didn't know what to do, so now I have the bottom, and now I'm working from the bottom going up. This is the idea I mentioned, burning the candle from two ends. Start from the top, simplify as much as possible. When you can't simplify and you're stuck, start from the bottom, simplify as much as possible. When you can't simplify, you've simplified things as simple as possible, normal form. If they're the same, you're done, right? So I simplified odd 0 to false, and now I don't know what to do with false anymore. I have no clue what to do with false, so I'll just stop. I'll go to the bottom. I know what to do with even 0. Even 0 is true. So let's say that 0 is even, okay? And now I have false and true. Well, that's just definition of false, all right? And let's always check, and everything's green. Life is good. So somebody asked, I don't know how to prove the base case. So the base case is you look at the formula, right? In this case, our formula is odd n equivales not even n. And you replace every variable that you're doing induction on, in this case n, with 0. So our base case was, here's odd n equivales not even n. This is it. Now we replace every n with 0. So this becomes a 0, and this becomes a 0. Okay, and we can send that, and CalCheck says, yes, this is what we're proving. So I communicate this, and CalCheck says, yes, you are proving this. All right. So if you want to know, let me know. Somebody asked, how do you know when you need to do a nested induction? Essentially, when you get stuck and you're like, oh, I can only use this definition if I knew the shape of a variable. If I knew it was 0, I could continue my proof. If I knew it was a successor, then I could continue my proof. Whenever you're like, oh, I can make progress in my proof if only I knew the shape, then you do induction, okay? So sometimes you do an induction proof, and then halfway through you're like, I wish I knew, is this a 0 or a successor plus 1, a successor? Then I could continue, and then you do another induction, all right? So that's when induction. So sometimes you don't need to do induction at all. Sometimes people will see natural number proofs and be like, oh, no, let me just do induction. And their life can be very difficult. So sometimes you don't need to do induction, just to let you know, all right? So let's do the second one. All right. Odd successor just says a number is odd precisely when the one before it isn't. They ping pong, right? Induction hypothesis. So even if you don't know how to write it out, you can just say end tab, and it will finish it for you. So induction hypothesis is sometimes you don't need it. Sometimes you're only looking at the shape of things, so you don't need it. All right. So I'll get to that in a moment. So sometimes you don't need induction hypothesis. Okay. So sometimes you do. So let's say here's the induction hypothesis. It lets me know that an odd number is not an even number, which is precisely the theorem. So I know it for the previous number. I'm working on successor of n, and I know for the successor of n, I know for the previous one, which is n, that the property holds. And then I just apply double negation. All right. All right. And everything works. Or yes, all green. Oh, no, sorry. Double negation would have removed the two nots. I apply even of successor to absorb one of those into a successor. Okay, and we're all good. All right. So let's talk about when you don't need to do induction. So Lukma, no induction hypothesis. Okay. So let's prove this theorem. N equals n. All right. Are you guys excited for this really, really interesting theorem? All right. Okay, so how will we prove this theorem? We'll prove it by induction on n. Okay, we need a base case, as always, and we need an induction step. Okay, on our base case, I'll have 0 equals 0, and then I'll do something, and then I'll have 2 down here. Okay, I can, of course, use reflexivity of equals. This is true. All right, so this is obvious. This is not a very interesting theorem. The reason I'm showing it to you is just to show you don't need to use the inductive hypothesis. Okay. The theorem statement. What's wrong here? I don't know what's wrong. The theorem statement variable cannot be applied to n in this proof. Why not? All right, well, when we don't know what to do, let's say we don't know what to do. We're proving suck n equals suck n. Yes. Suck n equals suck n. The theorem statement, a variable n cannot be specialized to the natural numbers in the proof. Well, that's interesting. This is the problem with doing live coding. You get these interesting problems you don't expect to get. All right. But I just wanted to show that it doesn't you don't always need the induction hypothesis, and unfortunately I have failed to do that. Someone is asking down here again why I used an equals instead of an equivalence. We can use either or. It doesn't matter, right? Somebody's asking back here again. Oh. Somebody's saying remove all of this. Okay, we can try that. No big deal. Suck n equals suck n, and then we can replace that with n equals n. But then we'd be using the induction hypothesis. So, so we could definitely follow this route. The difference between reflexivity of equals, I found out a lot of the times both theorems are interchangeable. Yes, because they're the same thing. They're the same thing. So here, let me get you to the big theorem list. So here's the big theorem list. Let me zoom that in for you. All right. So here's identity and here's reflexivity. All right. They're essentially the same because of equipollence or equanimity, which says all theorems are equivalent to true. So if you use identity, you can use it like this. But Q equals Q is true is the same thing as saying reflexivity, right? So I've tried to discuss this at length here for you. Try to explain why you can think of it in these two ways. All right. Let's go back here. All right. Are we all good? Okay. Okay. All right. So let's try another theorem. What kind of theorem do you guys want to do? Do you want to prove symmetry of addition, or do you want to move on? I'm not that picky. I'm good to either way. All right. Okay. So these are hopefully things. All right. So what is the interest? What do you guys want to do next? Otherwise, I can just continue doing more proofs on induction for you. Trying more or less. So here's addition. You can define addition on its first argument, right? If it's 0, we're done. Just return 0. If it's not 0, then take the successor out and then perform addition on the smaller arguments. Okay. So here's a very simple proof. 0 plus 0. Well, the first one is 0, so we're done. If it's not 0, we take the suck outside. Now we have a smaller value. We can apply induction hypothesis to transform that into m, and we're done. Okay. So somebody asked about 6.2. One moment. I don't understand 6.2, the last induction. Can you give us a hint? So let's look at this really quickly. So this was the previous slide. Let me just have it on the side for you. Okay. So the factorial is discussed in the book, I think, on the chapter of induction, right? So it looks like the numbers are screaming, like 0 is screaming, ah, right? And it's just a number of ways to list n different items, right? If you have 0 things, you have an empty list or an empty, if you have an n plus 1, then you pick one of those to be at the very front, and then you have n many ways to organize, n factorial many ways to arrange the remaining elements. So that's how we can define it inductively, all right? Here's just a cool little fact if you're interested about that we can extend this to the others. So here's the theorem factorial of 1, right? Really easy, I hope. So let's just do that. 1 factorial equals fact 1 equals the successor of 0. Successor of 0 factorial. Okay. Oh. What? Okay. Now we know definition of factorial. This is just successor of 0 times 0 factorial. This is now fact 1 equals successor of 0. So that's just 1 times 0 factorial. This is now definition of factorial 1 times 1. Okay. Could not justify step. Why? What couldn't it justify? Could not justify first step.
I think it's because you wrote 0 instead of like
sorry.
No problem.
Yeah. So I have like 4 different formalizations of induction right now. I have one that uses S instead of suck, one that uses capital Z instead of 0, and I need to remember to keep all of these in my head somehow. 0. Okay. Is that? Oh nope, I'm missing one right here as well. Thank you. Okay. And I'm missing one more apparently right here. Okay, sorry. That was unfortunately longer than I would have liked. Identity. Oh, I don't have identity. That's so unfortunate. Fact 1 times 1 equals 1. Okay. Calculate could not justify. No.
You might have right or left identity.
I'm sorry?
Yeah, you might have like right or left identity of
I did not have left or right identity. Oh, I did. You're right. Oh, wow. Okay. All right. Well, one day I will get faster live coding. So much pressure. All right. So we did one proof. Thank you for. We did the proof together as a group. Much harder when everyone's looking at me. Apparently, got to perform under pressure. Anyhow, use induction to show that all factorials are non-zero. Okay, let's do that. By induction on there's only one variable, so let's do that. Here's a base case. Let's do an induction step. Okay, let's check everything. Great, nothing broke. Now we need to have 0 factorial is not equal to 0. And this is equal, let's apply the definition of factorial. That gives us 1 is not equal to 0. And does anybody want to guess the next step? This should be a fact somewhere, that 1 is not equal to 0. Right there, 0 is not 1. Oh, had it the other way around. Sure. Okay. And then let's do the second one. Successor of n factorial is not equal to 0 equals, because of reasons, to the successor of n times n factorial is not equal to 0. Equals, okay. Does anybody know what you should do? There's a theorem that says things are not 0 precisely when one of them is not 0. Where is that theorem? Zero product, right? So something is 0 precisely when one or the other is 0. Okay, so let's apply that. 0 product. Actually, we need to get rid of that negation first. Definition of difference from says it's not the case that successor of n times n factorial equals 0. Okay. And that's the same thing as successor of n equals 0 or factorial equals 0. I'm missing some stuff here. Definition of factorial. This is, what is this? 0 product. Okay. Okay. So there we go. Do you want me to continue the proof? Somebody's asking other stuff. Okay. All right, let's finish this up then. Who knows what the next step is? Does anybody want to guess?
Have to say like 0 is not a successor.
Okay, yeah, we could do that. That's a good idea. Let's do that. 0 is not successor. That gives us false, or n factorial equals 0. I was going to say let's use De Morgan's, but I like your idea better. All right. Does somebody else want to tell us what to do next? Does somebody want to tell us what to do next? Or not?
We take the identity of or.
Excellent. And does somebody else want to tell us what to do next? Does somebody else want to finish that part? So here somebody says we do the identity of or. Great. Okay, what do we do next? What do we do here?
Induction hypothesis.
So this is not the induction hypothesis. To go from here to here, we'll do the definition of inequality, and then we can do the induction hypothesis. Okay, and it's all green, and green is great. We're using some theorems that haven't been proven, but that's fine. Okay, so that was a fun little proof. And I'm getting a bit faster. We'll try to get you the midterm marks ASAP, hopefully before the next midterm. All right. So let's see what else. What else do people want to do? Somebody wants to do cell 15. Let's go look at cell 15. 0 product. Ooh. Okay. All right. So does anyone know? So let's do cell 15. 0 product. The hint is to do a single induction. Does anybody know which one we should do induction on? All right. All right. So a lot of people are saying A. Does anybody want to tell us why we should do induction on A? Okay, so the reason we'll do induction on A is because the definition of multiplication is inductively defined on the first argument, which is A. So that's why it's a good idea to try A. Okay, so let's do by induction on A. Base case, induction step. Okay. The base case. All right, now we have an equation. Should we start from the left side or right side? Where should we go? Or turn the whole thing into true? Does anybody want to take a guess? Turn the whole thing to true? Sure, we can try that. No problem. When you don't know what to do, turning everything to true is usually a good idea. Let's try right 0. And that will give us 0 equals 0, equivales 0 equals 0, or 0 equals b. Then does anybody know what the next step is? So there's essentially only one step next. Does anybody know what that is?
Reflexivity of equals.
Excellent. Does somebody else want to shout the next step?
Identity?
That is not the identity.
A 0 of or.
Exactly. So what does 0 mean? 0 means I absorb everything away. Okay. And then here we can do identity. All right. Could have also done symmetry. 1 out of steps not justified. Oh no. Right 0, because that is not the right. That is the left. And this is why it's a good idea to have calc check around. Could not resolve theorem reference left 0. Ooh.
I think it's a definition of multiplication for 0. I think it's
yes.
like, yeah.
Thank you. That one. All right. I like you guys talking and helping me. You know, when you do this in programming, it's called pair programming, when someone types and someone else tries to help out. So I'm glad. If you guys would like more of this, please let me know, and we can do this more often. I can definitely get, over, I can overcome the pressure of having to perform in front of all of you. So let me know if you would like me to do this kind of stuff. So what should we do now? Should we pick the left side, the right side? Should we turn the whole thing to true? All right. Yes, Iman, equality has higher precedence than or. Thank you, James, for replying. So what do you guys want to do? Start with the whole thing and turn it to true? Start with the left side, start with the right side. What do you want to do?
The whole thing?
The whole thing? All right. Yeah, when you're stuck and you don't know what to do, you can always do the whole thing. Actually, why don't we be a bit adventurous? And let's start with the more complicated side. Which side has more symbols? So this side has 1, 2, 3, 4, 5. It's got 5 symbols. This side's got 1, 2, 3, 4, 5, 6, 7. Why don't we start with that side, because it has 2 more symbols, and see how far we get. Okay. And of course, when we get stuck, we can always burn the candle, right? Another reason of doing that is then your lines don't get so long, right? So let's do that, and A is a successor. All right, so what's the very first thing we do? Does anybody know?
0 is not a successor.
Muy bueno. Now what do we do? Does anybody know how we should continue?
Identity of 4.
I'm sorry? Yeah,
Identity of 4.
Good job. And then what do we do next? So now it looks like we're stuck. We have 0 equals b, and we're just stuck. We don't know what to do, right? Like there's no obvious way to continue. So now we go to the very bottom and say, let's put the other side here, right? This is that thing I keep mentioning called burning the candle. We started at the very top, we simplified, and now we're stuck. And you're on a midterm, you might not have the time to erase everything and start over. Right? You might not have the luxury of this extra time. So what you can do is say, let me go to the other side of the theorem I'm proving, put that at the bottom, and try to simplify that. Okay? And, pray to God this works. Okay, so what do we do here first? Well, how do I get up here? I think this will work. Okay. Could not justify this step. The successor of A times B is B plus that. Okay. All right. So now we're a bit closer. We still don't know what to do. So, okay, but we're at the bottom and we're working up now. All right. So what should I do next? Does anybody know?
You can use zero sum that you proved earlier on the 0 equals b plus a times b.
Yep. All right. What should I do next? All right. Does anybody know? Okay, so everything's still green. We're all good. Does anybody know what we should do next? So there are a lot of ways to progress, and I'm just curious. What do you guys think we should do next? All right.
You could use the definition of multiplication for a successor.
So I'm right here, and we're working up. So we don't know. How do we simplify?
Can you use the induction hypothesis?
Yeah, so I can use the induction hypothesis, but I just want to, so this is an aside, just an aside. I just want to show you what else you could do. This is an aside. We will definitely do the induction hypothesis, but, and we'll get to this at the end of today's slides, okay? So you're right here. What you could say is, hey, B is equal to 0, right? There's a B right here. Let me replace that by a 0, all right? I know that B is equal to 0, all right, and some other information. Because I know B is equal to 0, I can use this contextual information to help me in my proof, okay? So this is what I was talking about for today. This is called the replacement, right? I know these two things are equal, so if I have the left-hand side, I can replace it with the right-hand side, okay? So this is the idea, this is an immediate consequence of Leibniz, but at the formula level instead of at the inference rule level, right? So now, so if I have B equals 0, I can replace all the B's with a 0. And now this is just write 0 of multiplication and I'm done. Does that? So that was a very happy coincidence that this popped up. Okay. So, but yes, we can also apply the induction hypothesis, which says 0 equals A, lower 0 equals B. So the end of that aside. Okay. And what do we do next? Does anybody know what to do? So we can probably get rid of both of these in one step. So who knows what do we do next?
Write 0.
We're right here. We can't apply a write 0 rule.
You can use distributivity of and over or.
I could. I thought I had access to absorption. Absorption. There you go. Okay. So instead of, so it helps to know these theorems. Because we know absorption, it tells us if you have something and that same thing and or some other option, then you really only have the first option. Okay. So just this is what absorption says. It says if you have P and you have Q or P, well, if P is true, then this part goes away. Oh, sorry. And this whole thing becomes true. So if P is true, the whole thing is true, i.e. the whole thing is P. If P is false, then false and anything is false, and so the whole thing is false, so it's just P again, right? So the whole thing is equivalent to P. Okay, so this is absorption, all right? And I argued using truth tables for you, but really you can prove it again by using distributivity, okay? All right, so that was really cool that we did that. And it was very happy coincidence. It brought us to Leibniz. Let me just make sure there was nothing else I wanted to talk about here. So these are slides we've already covered. Just on indentation, Monis, you know, definitely a fun one to try. Implication, so we talked about how that's just an ordering, right? P is less than or equal to Q means the minimum of P and Q is P, right? So P is less than or equal to Q means minus Q is less than or equal to minus P, right? So stuff you're familiar with, okay? But now at a different level. P is at most the maximum of P or Q, right? If I have two things that I want to take their maximum, the maximum is bigger than the first thing and the second thing, okay? If I take the minimum of two things. The minimum has to be, well, smaller than both of those things. Okay, so a lot of these rules are kind of intuitive when you think about them from the lens of numbers. Okay. I think 362 is one of those important theorems to remember, like 332. I think 362 is kind of important. 363 is also cool, but 362 and 365 are really, really helpful to know. Super, super, super helpful. 362 and 365, yeah, because of reasons. All right. Yes. So try proving 362. Try proving 365. Fun stuff to try. Does anybody want me to try proving either of them for you? All right. Key phrase being try. Does anybody want to try or no? Yes. Somebody said yes. Well, whoever just said yes, you're going to help me prove this theorem. So let's prove 362. Theorem Zany Adventures. Okay. Let's try showing P implies Q equivals R equivals P land Q equivals P land R. There's a proof. Okay. All right. Well, we don't know what implication means, so that's unfortunate. So let me just quickly declare implication. Declaration. You should never do this, but I am not in a sufficient notebook to do that. There you go. So I just declared it. So this is the thing. Let me provide a definition for it. Definition of implication. P implies Q equivals P land Q equivals P. Okay. So definition of implication just says P is at most Q precisely when the minimum of them is P. All right. So now we can begin our proof. Let's begin with, this is the thing we're looking at, and we're trying to simplify it as much as possible, right? Because that sounds reasonable. Okay. Okay. Well, the only thing you can do with a new operation is, well, apply its definition. Which is not here. It's unfortunate. So notice it didn't pop up because it was in the same cell block. If it was in a different cell block, then it would pop up. So if I move it here, Command V, now it would pop up when I try to look it up. So now it pops up. So it needs to be in a different cell block if you want it to be in the tooltips. So that says P and Q equivals R equivals P. Okay. All right. Well, the only thing we know about these guys is this semi-distributivity law. So that's very convenient that it's right here. So I'll just so this semi-distributivity of and over equivalence tells us P and Q equivals P and R equivals an extra P over here equivals P. Okay. All right. And we have implicit associativity, right? So I can just say identity of implication, and that will get me to P land Q equivals P land R. And I hope this all works. All right, praise be to the Lord. Okay, so we proved it. I hope that works. Wait a second. Yes, so somebody said, if you don't try, you will never succeed. Yes, please try. Will implication be on the next theorem? So I'll bring this back up here in case it was missed. So here is the plan so far. So hopefully we'll let you know if anything changes from this particular plan. All right. So H7 is on implication, but we said that H7-2 is probably not going to be on midterm 2. And if that changes, we'll let you know. Okay. Anyhow, so let's where were we? Okay, so we covered this, we covered this, we covered this. Okay, so here's some property names. Some of you are still not as comfortable. Please review these slides. They are posted on Avenue. What it means to be symmetric, what it means to be associative. On the lecture notes, I've tried to put some keywords So for example, like associative, and I've tried to explain why you would care about these things, right? Like when an operation is associative, it lets you avoid making choices. When an operation has an identity, then here's the benefits of having it. So please review some of these ideas. There are more keywords down here somewhere. I didn't mention them, unfortunately. You will find them somewhere in here, hopefully. But yes, so please be comfortable with these words. Like distributivity is a form of factoring when you need it to use it in that direction. So that's something that many of you should try to aim to be comfortable, please. So here's some more theorems about implication. Again, I recommend you try proving them, all right? A bunch of these are a form of absorption, right? Like this one is an absorption law. This one's like this is P and not P or Q. P and not Q or P, right? So all of these essentially become absorption laws. Some cool things to apply. If the maximum is at least the minimum, then they must be equal. All right, so this is the goal. Yeah, so essentially that's what the golden rule says. The minimum is always at most the maximum. So you can bring that in there and then use mutual implication and you're done. So not a big deal. Everything is less than or equal to itself. Everything is less than or equal to infinity. The only way for something to be at least true is for it to also be true. False is less than or equal to everything. False is like negative infinity. All right, so we've talked about this a few more times. We'll talk about orders as they come, but yes, try proving some of these. I think this one is a very useful theorem, 378, case analysis. All right, we'll see it again, hopefully, when we get to lattices, and then it will define the notion of or supremum, if you like, or least upper bound in the future. So this definition says or is the least upper bound. If R is above Q and R is above P, then R must be above P or Q. Okay, so it's the least upper bound for Booleans. Okay, ducks. I'm just running short on time, so I'm just trying to cover a few more in case that's, and then maybe we can get back to doing some induction or some more calc check, I mean. Okay, so here's just some more properties about if two things are less than or equal to each other, they must be the same. Right? If two things are actually the same, then one of them is less than or equal to the other. Right? This is just reflexivity again. If two things are less than or equal to each other, then they are equal. This one said precisely. Right? You can chain less than or equal to's to get to the first one is less than or equal to the last one. So this is really, really cool. Transitivity. Remember, we had transitivity of equals, which lets us say when you have an equation, an equational proof, the first thing is going to be equal to the last thing. Transitivity, hopefully by next week or the week after, means you don't need to have just equals out on the left column. You can have implications or less than or equal to's. So we'll get to that later on. And then this one says you can have less than or equal to's on the side and equalities, right? And then this one is just essentially the other way around. Okay, so these three they justify having implications on the left-hand side as well as equalities. Okay, we'll get back to them. So we talked about Leibniz rule as an axiom. If you're interested, this book right here is like a Pulitzer Prize winner. It's called Gödel-Escher-Bach, An Eternal Golden Braid, GEB or EGB, and it's got a lot of hippy-dippy math and a lot of Escher paintings. I don't know if I can show you one off the top of my head. There are a lot of cool things in here. So here is a bunch of ants. And what orientation are the ants on? It's like a Mobius strip. So I recommend this book if you're interested in what does truth mean and how do symbols have meaning, right? And the sad fact that no formal system can capture the complexity of the whole numbers. Like the natural numbers, 0, 1, 2, 3, no formal system will ever capture the entire complexity of the whole numbers, which sounds really, really sad and pathetic. You know, like humans, we've advanced so far, but the natural numbers are too complex to have in a formal system. So if you're interested. The book is written for a lay audience, so you don't need to know any math to read it. It also talks a lot about piano fugues, so about Bach music stuff, and also about paintings. So, and it has a lot about programming and the soul and the mind and chemistry. So lots of fun stuff. Again, the more you try, the more things will click in. So don't be too worried about having to memorize. Just try to do more stuff, hopefully. So this is what I talked about in one of our examples that came up, maybe here, I think. All right. About how you can, instead of using Leibniz in the middle of a calculation with reference to a theorem, you can use it as a contextual rule. So if I know E equals F, then I can replace every instance of E with F, right? But I can also think of it as a contextual rule. If I know E equals F in my context, so I have P with Z becomes E, then I can replace this E with an F, right? So here's my left-hand side. In this left-hand side, one of the things I know, because it's an and, is that E equals F. So everywhere I see an E, I can replace it with an F. That's what the right-hand side says. Likewise, here, if I know E equals F, then in my conclusion, I know everything before the implication. So I know all of this stuff in the conclusion. So I know, in particular, I know that E equals F, and so I can replace every E by an F. Okay, so let's try doing some of this in action. So here's a thing for you to do. Unfortunately, in the book, you can just say replacement, right? And everywhere there was a K, I can replace it with n+1. But in CalcCheck, you have to do an auxiliary step. You have to actually make it clear which variable you're substituting, which sub-expression, all right? So I have 2 minutes left. Let me try to show you an example. So here is a calculation. Let's show that A equals 0, because that's a fun stuff. A equals 0 is the same thing as, actually A equals 0 and A C dot B equals A, okay? So A times B is equal to A. When does that happen? When A is 0, this happens. So let's try showing that, all right? So the very first thing to do is to say A equals 0, and I'm going to replace every, So this is the contextual information I know, and here I'll say here's Z times B equals Z, and everywhere Z becomes A. Okay, that's just substitution. Okay, but now I can apply replacement, right? Replacement, and that lets me say I know A equals 0, so everywhere else, because it's an and, I still have this Z. But instead of Z becomes A, I'll say Z becomes 0. Okay, and then I'll apply substitution, and that will give me A equals 0, and 0 times B equals 0. And we know by definition of multiplication, this is A equals 0 and true, and we know by identity of and, this is just A equals 0. Okay, so we can do it like that. Somebody says, when you have to use the operation O plus, you should be using that operation. You shouldn't be using plus or times. O plus is another operation. It's a new operation we've given you, so you should definitely use that. So I've run out of time. But I would like to leave you with a variant of this one that you could try at home. Try showing A equals 0 implies A times B equals A. Okay, so when does this happen? When you have the knowledge A equals 0. So since I've run out of time, I'll leave you with that. Yes, have a terrific Thursday. And yes, let me know if you have any questions. I'll stick around. Okay, bye.